Sebastian, Maciel, Diaz, and Gabriel Perez. Together we are the SkillCourt defense. Okay, so we're designing an athletic training system aimed towards professional athletes as well as beginners and amateur athletes. The motivation we have with the design is to improve the skill sets of every athlete that uses the pad, and we plan on reaching this goal by integrating a feedback system into the pad that will record the training session for each athlete and then relay it back to them so they know exactly where they need to better themselves. Okay, so we're doing some research on different types of sensors. For position sensors, we're looking into resistive touch sensors. For velocity sensors, we're looking into microwave sensors using the Doppler effect. For force sensors, we're looking into piezoelectric sensors. The materials that we're going to be using for our pad starts with aluminum. We chose aluminum because of its lightweight characteristic, and also since we are students, it is a more accessible material for us. And any consideration for material was silicone rubber for us to embed our LEDs. But since this material proved costly to us and also the heavier material, we decided to substitute it with a layer of high impact foam. The second layer of high impact foam is going to be used to protect the electronics inside of the pad from the vibration and the force caused by the impact of the soccer ball. And we're going to have two layers of plastics. The first layer is going to be Lexan plastic, which is going to act as a surface the contact surface of the pad. And the second layer of plastic is going to be glass, which we use as a support for the force sensors so that the vibration doesn't affect the means.
The standards that we'll be using for this project are going to be from ASTM and Grant. From ASTM, we'll be using F2276-10, which relates to the regulations and standards that must apply to producing and manufacturing sports equipment for ages 12 and up. This relates towards the practice of whether the sports equipment is too sharp, it is stable to be placed in indoor and outdoor areas, how light it is, what materials are needed. And the second standard, F25-15, references several times to the previous standard and explains how to do tests and gather the proper data required to analyze if the quality of the equipment is good. Along with using Lexan 9034, because of its ability to deal with high impacts that we'll be seeing in the sports field of soccer for professional play. Along with this, we're actually using aluminum 52 and 6061. We chose this because of its lightweight capabilities, along with its high non-corrosive resistance capabilities in indoor and outdoor environments, because we will intend for this to be outdoors as well, and to be able to deal with the changes of the weather, and because of its high yield strength. This is the first prototype design for the SkillCourt pad. As you see, it is made entirely out of wood. This is non-ideal for what we want for the SkillCourt pad to be. We want to have to be both indoor and outdoor because of the changing of weather and the changing of humidity and all these parameters. It will erode over time and it will fail. Along with this SkillCourt pad specifically only has one force sensor implemented into the device. This is not what we desired because the force measurement will be inaccurate with only one sensor being used. And furthermore, the pad itself is inside the frame and is only loosely fit in. This, after several impacts, will cause the pad to fall out. This is obviously not what we want for a final product. As you can see, this is our current product design. As you can see, it's very small. It was right there, if you wish to pass it along. As you can see, we made it smaller so that we test out the electronic components at the moment. A few of these electronic components that we wish to implement are that we have two force sensors into the design. This is for the requirements that our wishes for us to have, which is simulating the passing of a soccer ball from either the left or right side of one soccer player to another. This will help training for passing of the ball for a much more efficient game plan for the team. Along with this, because we want to have two strike zones left and right side, we'll need the two force sensors to distinguish whether the ball is hitting the left or right face of the faceplate, and along with giving a more accurate reading of the force being imparted onto the faceplate than to the prior design. Along with this, because we're having a smaller scale design for now, we want to see how we're going to implement different layerings of materials to see if we can make it more lightweight, so when we make it larger, we're going to have a much more lighter design for both the elderly and young to transport as well, apart from professional players.
For our future prototype, we are looking to introduce all our functionality. For one, we are looking at multiple strike zones. This is represented by the purple lines, and in the small scale, we have a green and a red side during certain sequences. This is to allow passing, as was discussed, and this will be determined by the position of our force sensors, which is represented by the red circles. Multiple force sensors can be used to provide a higher accuracy of force reading. We are going to include an ambient light sensor. This will adjust the luminosity of LEDs depending on the local lighting conditions. We're going to include a velocity meter at the center by the green square. This is to determine the velocity of the soccer ball upon impact. And we are looking to improve portability of the design by reducing weight. To achieve these features, we are going to be including these electronics. To gather all of the incoming sensors, we will be using an Arduino microcontroller, namely the MKR 1000. This will take all the force readings, velocity readings, and local lighting conditions, and output information to the user. We'll be using the force sensors and velocity sensors to determine the player metrics. We'll be using a photoresistor to determine the local lighting conditions, and we'll use LED strips as a user system interface to determine the current sequence. For our design, we will be looking at implementing a standard professional player stance. This means that we will be using a 36-inch wide by 15-inch tall striking area. The enclosure of our design will be made out of aluminum. It will be 1 inch in thick, and it will be surrounding the internal layers. For the first two layers, we have Lexan and plexiglass, respectively. It will be 3 32-inch thick, and we have 2 layers of high-impact foam at 2 inches thick each. For our analysis of our design, we used a SolidWorks static system. We applied a fixed geometry support on the rear panel, and we denoted each layer as a no penetration contact. This allows relative motion between the layers. We applied a 315-pound force at the center of the striking surface. This represents an average professional soccer player kick. After the simulation, we determined a minimum factor of safety of 2.61. What this represents is under professional play, failure would not be expected. The cost of our total design is roughly $250. $110 will be used on the materials alone, and $140 will be used on the electronics.
With regards to global design, our project motivation is driven forward by the increasing presence of technology in the athletic world. For starters, we intend for people of all ages to be able to use the pad. The pad will be able to execute play at both professional and amateur skill levels, as well as play at professional and recreational levels. We intend for the pad to be adaptable to many environments and climates found throughout the world, and we believe the pad has the potential for physiotherapeutic and rehabilitative practices. This is our Gantt chart. Over the last 4 months, we began by forming our team and taking on the project. We recently finished a small-scale prototype as proof of concept and analysis for a full-scale prototype. Moving forward, our project would hopefully lead us to having an initial prototype done by this year's end, and then improving that design in response to professional athletic fatigue, and finally manufacturing a minimum viable product.
You're open to questions?
You go ahead.
So you guys said that you researched the testing requirements for a system like this? You said you guys use some standard F2?
Standards that we use specifically, there is no actual product that we see in the market right now that is similar enough to what we've been asked to design and create. So we just wanted to see what is a broad standard for just normal sports equipment that we see around the world, basically punching bags, the vault beams and whatnot. So we just want to have an actual standard to follow for regulation purposes.
So the things you just described are all, comprise electronics? And I'm concerned that
No, that's not true because, for example, we were looking into punching bags. There are certain punching bags, high-end punching bags used for professionals to measure the force that's being imparted onto the ball is actually be attached onto the stem of the punching bag, giving them a reading and seeing if they're keeping with the momentum and essentially
So my question comes in of, do you guys plan on doing any like dynamic testing on your model, on your actual device? Because I would think that using, you guys using Arduino or?
Arduino.
Yeah, so I would assume that doing that, you guys are probably gonna either solder wires or use jumper cables to that board. I'd say that after probably 100 hits, your board's not gonna work anymore because your solders will probably break or your actual PCB will stop functioning just from the shock events. And I don't think you have characterized how the shock propagates into your system without, like, well enough to know that your product will actually survive like a lifetime or whatever your lifetime is. And so I think you guys need to look at ways of like providing stress relief to solder joints in your board and how to mitigate shock propagation into your electronics, or your product won't work past several hundred cycles, which to me seems like it's not going to be a viable product.
Yes, that is a valid concern. We will be looking at doing a vibration analysis.
I would not do a vibration analysis. There's nothing like, first of all, shock and vibe are completely separate. They're completely different types of loading on your system. And analysis for something like that is very spotty because you have nothing to actually ground your data on. Like, you're just feeding it random sine waves and you don't really know if it's representative for what it's going to see in real life. And unless you can like instrument something up and see what your actual readings are on the prototype, and then you can run analysis on that, your analysis really won't do anything for you.
That's something we will have to take into account. Yes.
I mean, under the same logic pathway, the foam that you're using with repetitive utilization may compress, and that may change everything. So, again, strongly suggest you do some testing. Verify that the system can survive at what would be classic load conditions with many repeats. Because someone's going to buy into this, going to want to use it every day, use it all the time.
Any other questions?
Did you mention the heat effects?
We have not.
Heat effect on the foam. So I'm guessing you're going to use this outdoors as well?
Yes.
Foam tends to lose it becomes brittle after long exposure to heat, as well as time. So you might want to understand what happens when you leave your foam outside in 90-degree weather, humidity, see how that affects it. Same thing of what kind of insulation you have on your device, so that whether it's dew from the grass where you're putting this, or like rain or anything like that doesn't get into your electronics.
And I think the other thing is using 6061 is a good measure for corrosion resistance, but unfortunately that doesn't actually work as well as we would like. So I think that anodizing your surface would be a good way of helping to extend that, especially because if you're going to use it outdoors, and like just mentioned, like there's dew on the grass or it's raining or something like that, you don't want a surface scratch kind of start corroding your aluminum, because that would be really silly. Especially because it would look really cool anodized because you can pick performance and colors, and it's a relatively inexpensive process. And it buys you a lot in terms of corrosion.
We were also looking into some sort of finishes or coatings that could be done to the enclosure to improve its thermal and weather resistant properties. We haven't gone in depth in it, so we have not reviewed that addition. Any questions?
Make sure those coatings are green. There's a lot of updating that's happening to coatings, similar to like Chrome, where they might have been legal and a couple of years ago, but not now. So just make sure that you check into what coatings are still